Hello. In this short video I will like to show you the electric nature of our reality. Professor will show us the experiments they conduct in 1968 to show us how the air could be demonstrated with electromagnetism. We will see how the molecules behave. This show us the much more real picture about our plane and the world we live in, and explain a lot of behavior in the natural world which heliocentric model doesn't provide us. We will not need fancy mathematics or physics. It is just electromagnetism. You can easily see how we need the barrier in order to a high pressure system to exist near the low pressure system. I hope you will like the video. Enjoy!
Suppose, for example, that I wanted to understand the behavior of molecules in a gas which I can't see, using something which I can see. Now, although we don't understand in the strict sense of the word magnetism, the behavior of magnets is familiar to me. So I'm going to use lots of small magnets to represent the gas molecules. Each of these magnets has been cut from a sheet of rubber which has been impregnated with barium ferrite and then magnetized. They're in a transparent box on top of a row of electromagnets. I'm going to put a transparent lid on top of the magnets and then switch on alternating current. The movement is exactly the same as the movement of gas molecules, entirely random. The lid lifts because of the impact of individual particles on it, and this is what we call the pressure of a gas. Now suppose that I move in a plunger from this end and compress the gas into half its original volume. Keeping the voltage the same, the lid now rises twice as high. And this is what we call Boyle's law. I can change the temperature of the gas by changing the voltage that I supply to the electromagnets. Let's try this. I can raise the temperature like this. Or lower it like this. Here's another demonstration you can do with this apparatus. If I take the lid off entirely, then I can show either evaporation from the surface of a liquid or the diffusion of gases. Individual particles will have fortunate collisions with their fellow particles and be ejected entirely. When smoke is introduced into a gas and then examined under a microscope, bright flecks of light are seen dancing about. This is known as Brownian motion. It's used as evidence of molecular activity, even though it's known that the molecules themselves are not being seen. The smoke particles are being buffeted about by the molecules. Now, I can put smoke into my gas in the form of paper balls, which will not be affected by the magnetic field. Put a lid on and switch on. And there is the Brownian motion represented in the analog. Now I'm going to connect up the motor in a different way so that the electromagnets produce their maximum flux at different times, and so that the whole effect shall be that of a traveling wave of magnetic field. Now watch what happens to the particles. We are effectively pumping the gas to one end of the box. Now, can we do this in real life? Can we pump gases without a piston? I suppose what I'm asking is, can we operate on individual gas molecules with a moving magnetic field? And the answer is that we can if we can strip an electron off each molecule. In this state, the gas is said to be ionized. Now, this whole process of gas pumping has the wonderful name magnetohydrodynamics. I'm afraid I can't show you MHD, as it's shortened to, very simply, but I can demonstrate that we can pump fluids, at least by pumping mercury rather than a gas. This trough has a piece of steel fixed into it to improve the magnetic circuit of this motor. When I pour mercury into the trough, it's going to flow underneath the piece of steel and be pumped along the bottom, up this end, and flow back over the top. Now, when I switch on the magnetic field, you can see the mercury making a small fountain at this end. It isn't easy to see mercury flowing, but you can float a coin on the river, and I hope that this convinces you that we can pump fluids electromagnetically. Now, this same magnetic field is much more potent if it operates on an aluminium sheet instead of on the mercury. The reason for this is that aluminium is about 40 times more conducting than mercury. Of course, I could make it more potent still if I could put some steel behind the aluminium to improve the magnetic circuit. But instead of this, I'm going to change the shape of the motor. Can you imagine that the two sides were bent upwards and the whole thing rolled up into a tube? Having imagined that to be done, let's make a machine that looks like that. We should find that the windings are very simple, being only a row of coils like this. The moving part is a steel rod with a copper sleeve around it. We put it in the end of the tube and fire. Well, that wasn't a bad shot, was it? This electromagnetic gun seems to have taken us right back to the start with our rifle. It looks as if we can make an electromagnetic model of nearly anything. We've certainly managed to reproduce the gun, but can we also reproduce the target? Can I float a ball on a magnetic field in the same way that I floated the ball on the water jet? Well, here is a ball. It's made of aluminium, and this is going to act as our jet, a single coil which is going to carry alternating current. I switch it on. The ball is certainly trying its best to float. But you see what's happening? It's like trying to balance a pencil on its point. What we need is some inward force which is going to make it drift back every time it tries to get off center. There seems to be no equivalent of the surface tension we had with the water jet. Now, inside this coil there is a second coil, and I'm going to feed this with alternating current of a different phase so that I can produce an inward traveling magnetic field which I can detect with our rotatable cylinder. Notice that the bottom of the cylinder is always moving inwards. And now, when I replace the ball, it does. Now, it's one thing to float a ball as big as this, but what sort of apparatus should we need to float a ball this size? It's a different world, you know, from the world of ping pong balls. Barry, if you just come and take the ball back slightly, we can see what we've actually got. Now, this is a sort of exaggerated version of the small ball coil. The inner coil is set down deeper in relation to the outer. First of all, we're going to send current through the outer coil only, as we did before. Would you like to come on the switch, please, Jim? Now, Barry, you and I have got to catch it, otherwise it might damage itself by falling back. Ready, Jim? 3, 2, 1, on. Right, lower it, Barry. Let's try and balance it. No, off, Jim. Again, it isn't stable with a single coil. Could you connect the other coil, please, Jim? Now, would you take the ball away, Barry, please? Now, I'm going to check the phase sequence of the two coils using a rotatable cylinder, which I've used before. What I want to happen is the magnetic field to go down the outside of the cylinder and so rotate it in that direction. So I want to see the cylinder spinning that way. Switch on, Jim. Switch off, Jim. That is the correct direction. Now, Barry, if you could have the ball, please. Now, this time, it shouldn't drift off. This time, you should fairly be able to see the magnetic flux spraying off the sides like you did the water from the ping pong ball. It might even spin for us. You can never tell just what this ball's going to do. If it spins, then we shall indeed have come full circle in the circle of magnetism. Ready, Jim? 3, 2, 1, on.